Today's lecture is on the introduction to earthquake-resistant design of reinforced concrete structures. Before we start our today's lecture, if you have any question in the previous topic, you can ask your questions, please. अगर कोई क्वेश्चन हो पिछले टॉपिक के डिस्कशन में जो हमने डायरेक्ट डिजाइन मेथड पे किया प्लेट स्लैब्स, उसके हवाले से कोई क्वेश्चन हो तो यू कैन आस्क योर क्वेश्चंस. If there are no questions, then we will go ahead with this today's lecture. Please. Okay, if there are no questions, then let's start today's lecture. Today's lecture consists of an introduction to earthquakes and its effects on buildings, and then earthquake design philosophy, seismic loading criteria, and there is one example on the static lateral force procedure, and a topic on gravity versus earthquake loading in reinforced concrete buildings. At the end, there are ACI special provisions for seismic design, which are very important, and then there are ACI provisions for special moment resisting frames, SMRF, and ACI provisions for intermediate moment resisting frames, IMRF, miscellaneous consultation, and then there is one design example on the special moment resisting frame. Objectives of this lecture are that students will be able to explain effects of earthquake loading on buildings, classify moment resisting frames, analyze story shear using static lateral force procedure, and evaluate RC members for SMRF provisions. Okay. You know these things from the engineering seismology, that Earth is composed of several layers. The uppermost part of this layer is called as crust. And then we have mantle, outer core, and inner core. And then within the crust, there are two layers. The topmost layer is called as lithosphere, which is the rigid part. And this lithosphere, rigid part, moves over asthenosphere, which is a relatively soft layer. Litho means stone, sphere means layer or portion. So this is the relatively rigid portion. Astheno means without strength. So this is part of the crust which is without strength, softer layer. The lithosphere, part of the crust, moves over the asthenosphere, and the tectonic plate movements occur due to this lithosphere movements. And this is a picture of the world map, where you can see these lines. These red lines basically show the boundaries of the plates. I hope you have studied all these plates movements in the seismology course. And there are 7 big and several small plates on the earth crust. And then there is movement of these plates. The movement can be then divided into 3 movements. One is the convergent movement, and the boundary at the convergent movement is called as convergent boundary, where 2 plates move towards each other, and it's a kind of convergence occurring at the boundary. So this is called a convergent boundary. You can see in this map, this is the Indo-Australian, this is the Indo-Australian plate. And this Indo-Australian plate is colliding, head-on colliding with the Eurasian plate. Indo-Australian plate and Eurasian plate collision is causing this Himalayas range convergent boundary. And when the energy is stored due to this movement, then the energy is stored as elastic strain energy, and if there is sudden fracture below the earth crust at any part of the plate, then this energy is released and earthquake occurs. You know these things, okay? And most of the earthquakes occur along these boundaries, convergent boundaries, okay? And then there are divergent boundaries where the two plates move away from each other. You can see divergent boundaries occur in the ocean, like these, the divergent boundaries. The divergent boundaries, usually there are no earthquakes. You can see there are no darts. You can no darts at divergent boundaries, okay? And then there are transform boundaries where one plate move past another plate, and this is the sliding of one plate against another plate happens at several locations on the Earth map. This also this transform boundary also causes storage of the elastic energy, and when there is some fracture deep down the earth crust, then this energy is released and earthquakes occur. When earthquake occur, then the movement taking place at the fault lines causes energy release, which is transmitted through the earth in the form of waves. And these waves reach the structure, causing shaking. You can see by this from this figure on the left that when an earthquake occurs deep down the earth crust, and then the energy is released, the energy travel to the surface of the earth, and then these movement of the top layer of the earth, this is shaken, and this shaking and movement of the ground at the top surface of the earth on which a building rests moves, then the ground, the foundation which is attached to this upper surface of the earth also moves along with this movement of the ground. When the foundation moves, the rest part of the structure cannot move along with this movement due to the inertia. And due to the inertia, the upper part of the structure lags behind this movement of the ground or foundation, which induces stresses in the structure. And it is these stresses which causes bending movements, shears, and other form of effects in the structure. And the structure must be capable of resisting these stresses, otherwise it may collapse. Okay, the point where this energy, where this breakage of the or rupture occurs is called as focus. Okay, and the focus projection on the surface of the earth is called as epicenter. The depth is called as focal depth, and the distance from the epicenter to the place of interest or building is called as epicentral distance. Okay. The seismic events around the globe mostly take place at the boundaries of tectonic plates. You are well aware of these things. These are the dots which have been shown in this figure, indicating that most of the earthquake events, they have occurred along these boundaries, further substantiating this fact that earthquake occurs due to the movement of tectonic plates. These are types of waves, you know, these, you must have studied these type of waves in the seismology course. There are body waves and surface waves. Okay, body waves are further classified into two: is P and S waves, compressional and shear waves. P waves are called as P because they are push and pull waves, and S waves are shear waves, up and down, side to side movement can occur. And then there are surface waves. Okay, for engineers, what is important is that when these waves reach the surface and they hit the structure, regardless of the type of the waves, then this movement of the ground, the movement of the foundation along with the ground, will cause stresses in the upper part of the structure, and the structure must be designed against those stresses induced by this movement. The seismologists study these waves for other purposes. Okay, you would have seen and you would have studied those in the course of seismology. Okay, now when an earthquake occurs and the surface of the ground on which the foundation of our structures rests moves along with the ground, as is being shown in this figure to the left. You can see this structure is resting on the foundation, and the foundation is attached to the ground. When the ground moves, because the ground is attached, the foundation is attached to the ground. So when the ground moves, the foundation must move with the ground, because there is friction between the foundation and the ground, and the friction is so high that sliding between the foundation and earthquake moment cannot occur. The sliding between the foundation and the ground cannot occur. So they must have to move together. So when foundation moves together with the ground, the foundation is attached to the upper part of the structure. So the upper part of the structure should also move along with it. If the upper part of the structure had moved along with the foundation, there would have been no stresses induced in the structure. But as you know that the upper part of the structure, due to inertia, cannot move along with the foundation. So this would induce stresses in the upper part of the structure. You can see that the foundation moves by this amount, this much displacement, and the top of the building, the roof of the building is here. So this causes the relative displacement, and you can see now the shape of the building where you can see a bending in the wall. So this bending in the wall is basically the stresses. The bending in the wall basically introduces or induces stresses in the walls. On the right, you can also see another frame structure with two columns. When the ground moves, the foundation moves along with the ground, but the roof cannot move along with the ground due to inertia forces. And inertia, you know, is the property of material due to which it stays. It tends to stay at its initial or original position. So the roof lags behind the foundation, and this lagging behind is equal to this relative displacement. If total displacement here is, for example, 4 inch, and the roof moves only by 2 inch, so 4 minus 2, this 2 inch is relative displacement, and it is basically this relative displacement between the ground and the roof which will cause stresses, which will produce stresses in the lateral load resisting elements. The lateral load resisting elements are columns, are walls. Why in the lateral load resisting element? If you look at this picture, there are many concepts which can be explained through this simple picture. The roof moves. When the roof moves laterally, so the possibility of the possibility of inducing stresses within the slab, they are negligible, because mostly the roofs are very rigid, and when the rigid bodies move in the same plane, then the stresses can not be induced. And the columns and walls, they are attached between the roof and the ground. And when the ground moves and the roof tends to stay at its original position due to inertia, so this lagging behind of the roof from the ground produces this displacement, relative displacement. This relative displacement will cause stresses in the columns, not in the roof. Okay. If the displacement of the roof had been equal to the displacement of the ground, the foundation, there would have been no stresses. In other words, if this U is 0, which is the relative displacement, then the stresses in the columns will be 0. For this reason, if the structure is very, very rigid, which means that if a structure is very short, low rise, and the columns and the walls are very thick and long, then it is possible that the roof of the structure would move along with the foundation and no stresses would be induced in the walls or columns. And there is another way in which we can remove or eliminate the the stresses produced in the columns and walls. And that is if we can devise a mechanism where when the ground moves, the foundation does not move with the ground. So if we are able to place some material between the foundation and the ground, and the material is so flexible and soft that when the ground moves, the foundation stays at its original position, then the movement will not be transferred to the foundation, and this movement will not be further transmitted to the upper part of the structure, which is called as base isolation. So when the base of the structure is isolated from the ground, then we also can reduce the stresses, or we can completely eliminate the stresses in the upper part of the structure. Okay. Short of doing these two things, by this I mean that if we cannot do these two things, to make structures very, very rigid, or to isolate base of the structure from the ground, then we must have to design the structure in such a manner that all the stresses induced in the structure are resisted by the lateral load resisting elements, and the structure does not collapse. Horizontal and vertical shaking during an earthquake. We know that earthquake causes shaking of the ground in all three directions, and since the structure comes from the focal point or the focus deep down the earth crust, so the waves will move in all three directions, X, Y, and Z. In fact, they will move in many, many directions, in all directions, but they can be then resolved, all the vectors can be resolved into three components. Okay, and these three components are X, Y, and Z. X, Y are in plane, and Z is a vertical component. So X and Y will cause horizontal shaking, and Z component will cause vertical shaking of the structure. This vertical acceleration during ground shaking either aids to or subtracts from the acceleration due to gravity, which means that when there is an earthquake, so the vertical acceleration, which is basically a fraction of the gravitational acceleration, fraction means 0.1, 0.2, 0.3 g. This when multiplied with the mass of the structure, and during the earthquake shaking, if the acceleration direction is upward, then the total mass of the structure, or the weight of the structure which is acting downward, will be deducted from this upward mass, upward acceleration times the mass, which is a force created by the earthquake motion. So that will, at that particular instant of time, the weight of the structure will be reduced. And when the acceleration direction is downward, when the direction of the acceleration is downward at a particular instant of time, then the mass multiplied by the acceleration will create a force, inertia force in the downward direction, and this force will be added to the weight of the structure. This will aid to the weight of the structure, and the weight of the structure at a particular instant of time will be increased. These things must be taken into account while designing the structure. The structure are, however, normally designed for horizontal shaking to minimize the effect of damage due to earthquakes, and the vertical component is indirectly taken into account. Although in very specific cases or very specific designs, for example, the nuclear power plants, dams, and some long-span bridges, it may be a requirement that the structure is particularly analyzed and designed for vertical acceleration as well. Normally, the residential buildings and the journal buildings, they are not designed for vertical acceleration directly. They are only designed for horizontal acceleration, and vertical acceleration is indirectly taken into account in the design of the building, as you will see in the coming slides. Okay, the types of earthquakes. This again, you would have studied in the course of seismology that shallow earthquakes are those whose depth of focus varies between 0 and 70 kilometers. and deep are those where depth of focus varies between 70 and 700 kilometers. Okay, this is an important discussion with regard to the earthquake engineering. This slide number 14 and 15. There are earthquake characteristics with respect to distance from epicenter. There can be many earthquake characteristics, but three of them are most important for us. Number one is the distance from the epicenter. When the distance from the epicenter is around 25 kilometers. So within that radius, which is this one, within this radius, the earthquake characteristics are such that their period is very, very low, which means they are very high frequency. They are very high frequency waves, and they vibrate very vigorously. The amplitude is also very, very high, and the frequency is also high, and the duration of the earthquake is also more as compared to as we move away from the epicenter. So with the long duration of earthquake, within this 25 kilometer, long duration of earthquake, high frequency, and high amplitude of the earthquake. These are three characteristics of earthquake waves within this 25 kilometer. And this 25 kilometer radius, this zone is called a near field zone. This is a near field zone, and the earthquake characteristics are different in the near field zone than from the zone which is far than the 25 kilometer. Okay, so then in the range from 25 to 50 kilometer, there is another zone, and within that zone, the earthquake characteristics are such that the duration of the earthquake is also, as compared to the near field zone, is short, and the frequency is low as compared to the near field zone, and the amplitude is also short, small as compared to the near field zone. Okay, the earthquake waves are the same waves, but the characteristic of the earthquake waves will change as we move away from the epicenter. You know that you must have heard the word attenuation. Attenuation occurs both in all respect, with respect to time as you move away from the epicenter. So the duration of the earthquake decreases, the frequency of the earthquake waves also decreases, and the amplitude also decreases. So attenuation occurs in all these three characteristics. All these three characteristics of earthquake waves are very high, means the duration is long, and the frequency is high, and the amplitude is also high. And they gradually decreases as we move away from the epicenter. And they have a lot of effect with respect to the structural time period. This we will see that what is the effect of these waves characteristic for same type of building. For same type of building, they have different effect if they are located in different zones. Away from 50 kilometers, then they are called as far field, and which starts from 50 kilometers and above. Okay. Now we know that every structure has a natural time period, and this natural time period can be one or more, can be many time period. It's not only one time period that the structure would have. The natural time period of a structure in a particular direction will be different than the natural time period in another direction. The natural time period of a structure is its important characteristic to predict behavior during an earthquake of certain time period, resonance phenomena. For a particular structure, the natural time period is a function of mass and stiffness. You know this very well, that the heavier the structure is, the time period will be more, the less the stiff, the time period will be more. And they vary the square root of mass to stiffness ratio. However, T can be roughly estimated from time T is equal to 0.1 into number of stories for most of the reinforced concrete frame structures. So for example, if the structure is 4 stories, high, then the time period will be 0.4 seconds. Now coming to the near field, moderate field, and far field. Near field, intermediate, and far field. With respect to discussing the effect of the earthquake characteristic on the buildings. Okay, as we have seen in the previous slide, that the earthquake characteristic within the near field are such that the frequency is very, very high, and the time period is very low. Earthquake duration is long, and the amplitude is also high. And then we also said that the time period of a structure can be calculated from 0.1 multiplied by number of stories. So for example, if a structure is only 2 stories high, then the time period of the structure will be 0.2 seconds. 0.2 seconds. Okay. So within the near field, you would have seen on the slide number 14 here that the time period of the earthquake waves, the range of the time period for the earthquake waves. You know that earthquake waves are random in nature. They do not have one time period of one frequency like sinusoidal waves or other functional waves, but they are random in nature, and they actually have a range of frequencies and range of time periods. So within that range of frequencies and time period, the range of time period, we'll be talking in terms of time period because most students do not understand the explanation in terms of frequencies. They easily understand the time periods because the time period is the time taken to complete vibration. So the time in the near field region of the earthquake waves varies from 0.05 to 0.3 seconds, which means that the waves time period, there will be waves with a range of time period from 0.05 to 0.3 seconds. Okay, so when the earthquake waves time period is also 0.2 seconds, which is within this range, and the structural time period is also 0.2 seconds for a 2-story structure, then the possibility of occurrence of resonance is very, very high. Resonance can occur very easily in the near field for low-rise structures up to 3 stories because the maximum time period, which was shown in slide number 14, is 0.3 seconds. So for up to 3 stories, in the near field, if structures up to 3 stories exist in the near field region, then the possibility of occurrence of resonance for this structure is very, very high, and they are susceptible to heavy damage and probably collapse if they are being hit by even a low amplitude earthquake, because you know that resonance is a phenomena where the frequency of the forcing function, in this case earthquake waves, and the frequency of the object, which in this case is structure, they match. This match is called as resonance, and this is basically an in-phase motion. The same when the earthquake waves moves in one direction, so the structure also moves in the same direction, thereby increasing slowly and gradually amplitude of the structure, displacement of the structure, and finally can cause collapse of the structure. You would have heard several times a very famous example of resonance of the bridge and people passing over bridge. If there is a army contingent and if it is passing over a bridge, and if the soldiers when the soldiers pass over a bridge, and if there are steps motion, which will basically have some time period, if that soldiers steps time period match with the natural time period of the bridge, then there is a possibility of occurrence of resonance. Okay, every resonance is not dangerous. only that resonance is dangerous, which can reach the maximum limit of the structure, maximum resistance limit of the structure. So when there are 2 or 3 soldiers and their steps time period is the same as the time period of the bridge, then although resonance will occur, but it may not cause any problem to the bridge. However, if there are there are a lot of soldiers passing over a bridge, and if there is enough energy imparted by the steps of the soldiers to the bridge, only then the bridge can be in trouble. And this is the energy imparted by the soldiers' steps and the resistance of the bridge offered, which will then depend on the capacity of the bridge reaching its limit. Okay, so resonance with a small energy may not be dangerous. Resonance with a enough energy greater than the resistance capacity of the bridge of the object may create problems. Okay. However, if there is a case when there are many people crossing over a bridge, the number of soldiers is very high, but then the steps time period is not the same as the time period of the bridge, then it may not cause any problem to the bridge. Okay, so the frequency match, which is resonance, is also important, but then the energy imparted is also imparted, or the energy used in this resonance is also important, and low energy may not cause any problem to the resonating structure. Okay, if there are high-rise buildings within this near field structure, then resonance will not occur, but it does not mean that the structure will not collapse. You should clarify this concept, that if there is no resonance, it does not necessarily mean that there will be no collapse. The collapse can still occur even if there is no resonance, and that collapse can occur in the initial imparted energy, which is called as impulse energy. And this can be explained again from the example of the soldiers passing over a bridge. When the first step, the soldiers hit the bridge with the first step, and there are many soldiers, and let's say when they hit the bridge in the first instance, the first step may transmit energy to the bridge in such a big amount that the structure or the bridge collapses at that instant of time. So without resonance, the bridge can collapse. In the same manner, if there is an earthquake shock or wave hitting a high-rise structure in the vicinity of the epicenter in the near field region, so even without resonance, the structure can collapse. Okay. Now coming to the moderate intermediate field. In the intermediate field, you would have seen that the time period range is 0.3 to 1 second. So if the time period of the structure is such that it ranges from 0.3 to 1 second, then this is possible. The resonance is possible, and the structures may sustain damages or even may collapse during the earthquake. Similarly, in the far field region, the high-rise structures are more susceptible to damages because the time period of the wave and the time period of the high-rise structure can match in the far field region. Okay. If you have any question with regard to this slide number 14, 15, and 16, you can ask your questions. Or if there are no questions, we can go ahead.
अस्सलाम वालेकुम सर।
सलाम
सर अगर हमारे पास एक एग्जामिनेशन हॉल, अमीर हमजा।
امیر حمزہ پلیز.
سر اگر ہمارے پاس 2 اسٹوری ایگزامینیشن ہال ہو اور اس میں میزنائن فلور ہو
ہاں ٹھیک.
تو اس کی سر وہ ٹائم پیریڈ 0.2 اس کی ٹائم پیریڈ 0.4 ہوتی ہے. اس کی وجہ کیا ہے سر؟
اس کی وجہ زیرو آپ نے خود معلوم کیا ہے یا آپ نے سنا ہے؟
یس سر، معلوم کیا ہے یہ ٹیپ پہ سر.
یہ ٹیپ پہ معلوم کیا ہے. اچھا مجھے تو نہیں پتا کہ آپ نے کیسے معلوم کیا ہے، لیکن اگر 0.4 سیکنڈ آتا ہے تو اس میں ایسے کیا پریشانی کی بات ہے؟
سر تو وہ فارمولا جو ہے 0.1 ملٹیپلائی بائی اسٹوریز، تو اس کے حساب سے پھر یہ غلط نہیں ہے؟
وہ تو اپراکسیمیٹ فارمولا ہے نا. وہ تو اپراکسیمیٹ فارمولے تو ہمیشہ جب آپ ڈیٹیل میں کام کرتے ہیں تو اس سے ڈفرینٹ آپ کا ریزلٹ آ سکتا ہے. اپراکسیمیٹ فارمولے ہمیشہ اس لیے ہوتے ہیں کہ آپ صرف اندازہ لگانا چاہتے تو اندازے کے لیے ہوتے ہیں، وہ ایگزیکٹ تو نہیں ہے نا. مطلب وہ تو کسی 0.1 ہے تو 0.059 بھی ہو سکتا ہے، 0.12 بھی ہو سکتا ہے. تو یہ پریشانی کی کوئی بات نہیں ہے. اگر آپ کا 0.4 سیکنڈ آ رہا ہے اور آپ نے ٹھیک ٹھاک ماڈلنگ کی ہے تو اوکے، نو پرابلم. اگر اس سے ڈفرینٹ آ رہا ہے
سر یہ ڈپینڈ کس چیز
ٹھیک
پہ
ہے.
کرتے ہیں؟
یہ ڈپینڈ ماس اور اسٹفنس پہ کرتا ہے. آپ دیکھیں اگر آپ یہ تو صرف ایک فارمولا دیا ہوا ہے جنرل اسٹرکچرز کے لیے جس میں کوئی خاص قسم کا مسئلہ نہ ہو، لیکن ایک اسٹرکچر ایسا بھی ہو سکتا ہے کہ جو صرف سنگل سٹوری ہو لیکن اس میں ماس اتنا زیادہ ہو اور اس کا اسٹفنس اتنا کم ہو. اسٹفنس ماس آپ سمجھتے ہیں نا، ویٹ کو کہتے ہیں کہ ویٹ آپ کسی چھت کے اوپر ویٹ بہت زیادہ ڈال دیں. مثلا آپ نے ایک شو روم بنایا جس میں آپ نے ٹریکٹرز کھڑے کیے، بڑے ہیوی مشینری کھڑی کر دی اوپر فرسٹ فلور میں، اور چھت کے ٹاپ پہ چھت پہ آپ نے کھڑی کر دی، اور اس میں آپ نے دیواریں بالکل نہیں دی نیچے، اور کالم آپ نے بہت تھن کر دیے 12 بائی 12 انچ کے، تو وہ بڑا فلیکسیبل سٹرکچر ہو جائے گا. ان اسٹفنس کم ہوگی اور ماس اس کا بہت زیادہ ہو جائے گا، تو اس کا ٹائم پیریڈ ہو سکتا ہے کہ بہت زیادہ ہو، یہ بھی ہو سکتا ہے. تو وہ اس سٹرکچر کے لیے جو فارمولا 0.1 انٹو نمبر آف سٹوریز ہے، وہ اس قسم کے اسپیسیفک سٹرکچرز کے لیے جس میں جو عام سٹرکچر سے مختلف ان کے لیے نہیں ہے. تو آپ کا کیس بھی مجھے ایسا لگتا ہے کہ یہ تو عام کیس نہیں ہے نا، اس میں میزانائن فلور بھی ہے. عام سٹرکچر میں تو ایسے میزانائن فلور وغیرہ چیزیں نہیں ہوتی ہیں، نہ بڑے ہال ہوتے ہیں، بس 20 بائی 25 وغیرہ کے گریڈز ہوتے ہیں. اور ہاں، تو اس کے لیے یہ فارمولہ ہے. ٹھیک ہے.
اوکے سر.
اینی ادر کوشچن؟ کسی اور کا کوشچن ہے؟ Okay, if there are no questions, we will go ahead. You would have also seen these earthquake recording instruments, which are called as seismograms, and the seismograph. And the seismograph, they will basically record the earthquakes, and the record of this is called a seismogram. Using multiple seismographs around the world, accurate location of the epicenter of the earthquake as well as its magnitude or size can be determined. And the working of seismograph is shown. One of seismograph is shown in this figure. This is a seismogram obtained from a seismograph for an event. And you would have also heard the name Richter scale. This was basically developed by Charles Richter in 1935, a US scientist, US seismologist. And the Richter scale is logarithmic, which means that a magnitude of 5 Richter measurement is 10 times greater than a magnitude 4, because it is 10 by 10 or 100 times greater than a magnitude 3 measurement. You know these things, because there is no need to further explain. You can study the book of seismology. These are some famous earthquake records around the world. This is one of the famous record on top left, which is called El Centro in 1940 record, southeast component. And this is one of the most used record because the digital data of this record is available. So we use this record in our experiments on the shake table. On the shake table, when we test our structures, so we use this El Centro 1940 record because it contains various frequencies which are required for testing a structure. So this is a natural record. We prefer use this natural record in our experiments, El Centro 1940 record. The same is also used in our analysis whenever some specific analysis is required. We use this El Centro record along with some other sets of records. Okay, so you can see in many records, this is San Fernando 1971 earthquake, Parkfield earthquake, San Francisco 1957 earthquake. There is only one record at the bottom of this page, Mexico City 1985 earthquake, where the frequency is very, very low. You can see here in all cases, the frequencies are very, very high. Okay, but in this case, the frequency is very low. So this is a very unusual record, and because this record was obtained from around 300 kilometers away from the epicenter. So as we have discussed this quite in detail now, that the frequency of the earthquake waves will be very small as you move away from the epicenter. So this is a typical example of that because this record was obtained from 350 kilometers away from the epicenter. So low frequencies can be seen in this earthquake. And then due to this earthquake, 350 kilometers away from the epicenter, there were many tall buildings, and those tall buildings, time period coincidentally matched with the time period of this earthquake, and thereby damaging the structures. And it is a typical classical example of far field. Far field earthquake frequencies matching with the frequency of the structure and in the structure. Magnitude 6, which is basically almost equal to half earthquakes that occur. Magnitude 6 during a year is 200. But fortunately, most of these earthquakes occur in the ocean, and thereby causing no damage to the earth. Okay, you can see that even magnitude 8 earthquakes occur around 3 and 9, 1, and so on. The energy release is also shown on the right side. This is the seismic zones of Pakistan. The seismic zones of Pakistan are divided into 4 zones, and zone 2 is then further subdivided into 2 zones, 2A and 2B. The severity of the earthquake increases with the zone number. Zone 1 is a low seismic zone. Zone 2A and 2B are moderate seismic zones. Lower and upper moderate. Zone 3 is severe, and zone 4 is most severe earthquake zones. Okay, these zones are shown in the map. You can see that most of the Punjab province lies in the lower moderate zone, zone 2A, with this light blue color. Okay. Our Khyber Pakhtunkhwa, it lies either in zone 2B or 3, upper northern part of our province. They lie in zone 2, in zone 3. And parts of this is the Balakot region and Chatral region. Some parts of this, they lie in zone, even in zone 4. Similarly, Balochistan, most of the Balochistan region is located in zone 3, zone 2B, or some parts also in zone 4. Parts of Sindh mostly are in zone 2B, with some parts in zone 2A, and Karachi in subduction zone. So parts of this also are in zone 4. Before we want to design a building, so we know that this building, the building is designed in certain location. The location is also known to us. If it is not known to us, we cannot design the building against earthquake, because there are different seismic hazard zone in different areas. So the area in which the building is to be constructed must be known to us. Okay. The importance of architectural feature. Architectural features are also important because they will also either be an advantage to the overall structural resistance, or a disadvantage. For example, too tall structure, too long structure, and too large in plane. These are not good shapes with regard to the earthquake resistance. Similarly, these shapes, C shapes, curved shapes, or T and L shapes, they're also not good shapes because most of these shapes would cause torsion stresses in the structure, and to increase the capacity of the structure against the torsion stresses, this becomes very costly. So when the structure from the beginning is planned in such a manner that the shape is of circular or square or rectangle, then they are good shapes. These good shapes, simple plane with good shapes, they will offer good resistance to earthquake, and then the structures would be designed as economical structures. Otherwise, if it is a compulsion, if there is an urge from the client side or from the architecture side, or if there is some requirements, or if the requirements of the building are such that they must be placed in one of these shapes which are not good with regard to earthquakes, so even then they can be designed, but then they'll be uneconomical, cost will be high. At the planning stage, architects and structural engineers must work together to ensure that the unfavorable features are avoided and a good building configuration is chosen. These are also some undesirable scenarios where two buildings are constructed very close to each other. So there will be pounding of one building against another. This pounding can cause localized damages to the structure. Sometimes it is not possible to do this. Then there are some other means to overcome these pounding impacts. Slopy ground are also not desirable scenarios. Similarly, hanging or floating columns, where the columns are erected on cantilevers. So this is also not a good situation. This is another situation where the columns in most of the buildings which are designed nowadays, they have parking basements where there are no walls, and in upper floors there are walls. So walls will make the structures stiffer. The floors which contain walls will make that floor stiffer than the floors where there are no walls. So there will be a drastic difference from one floor to another floor in the stiffness of the structure, which may create a soft type of story, and which is not a desirable situation. This is shown in this figure. This is a figure where the top stories are very, very rigid, but the bottom story, because of this basement, there are no walls. It becomes flexible, so this can cause this kind of motion, and which can be detrimental for the structure. However, if the structure is designed by taking into account all these walls and these irregularities and the elements which exist in the structure, then they can be designed without any problem. The lower story or the basement columns then must be kept very, very stiff. Their size should be larger than the size of the upper stories, and then they can be designed. However, when we say that the situation is undesirable, so by this we mean that if this situation would have been avoided, then the structure would have been economical. This is an earthquake design philosophy explained on this slide number 26, which is also important to understand. But before we start discussing this earthquake design philosophy, we'll take a break of 10 to 15 minutes, and then we will continue our lecture after that. If you have any questions, you can ask your questions after the break. Okay, so now we will discuss the earthquake design philosophy. In the left figure, you can see 3 lines in the graph. Okay, this line is for the performance of hazardous facilities. The second line is performance for essential buildings. And the third one is performance for ordinary buildings. Keeping in view these 3 lines, now let's see the X and Y axes of this graph. On the Y-axis, you can see the earthquakes. The first part is the frequent earthquakes whose probability of occurrence is 50% in 50 years. The second part is rare earthquakes, where the probability of earthquake is 10% in 50 years, and very rare earthquake, where the probability of earthquake is 2% in 50 years. So with this keeping as origin, this part, when you move down, the frequency of the earthquake decreases, but the intensity of the earthquake increases. Okay, and when this keeping as origin, when you move towards the right in this graph, the functionality of the building decreases. So on the x-axis, there are different performance levels of the building, and on the y-axis, the earthquakes with regard to their occurrence and severity and frequency of occurrence is being given. Okay. So fully functional means that the building should remain fully functional if it is within this quadrant with respect to the frequent earthquakes, and it should remain operational, its life safe level and near collapse level. So for example, now coming to this fully functional level, the building should remain fully functional, or the performance of the building against a given earthquake shall be such that it should remain fully functional if the earthquakes are of such a nature that their probability of occurrence is 50% in 50 years, which means very low magnitude earthquakes. These earthquakes are very frequent. Okay, so against frequent earthquakes, which building should remain fully functional? The essential buildings, which means hospitals and schools and other public essential buildings, they should remain fully functional. And the hazardous facilities, for example, nuclear power plants or some other industries having hazardous chemicals whose leakage and breakage can cause mass scale destruction. So these two type of buildings, essential building and hazardous buildings, they should remain fully functional when they are being hit by frequent earthquakes. They should remain fully functional. Now, the performance for hazardous facilities, those buildings shall also remain fully functional against rare earthquakes whose probability of occurrence is 10% in 50 years. Okay, but corresponding to this earthquake, the essential building need not to be fully functional if they are only operational. So it is enough. What is the difference between fully functional and operational? It has been explained in this figure on the right. This you will see later. Then you have the performance for ordinary buildings. The performance for ordinary building shall be such to remain fully functional if they are only operational. Okay, and against rare earthquakes, the ordinary building shall be at life safe level. If they get damaged in an earthquake, so the level of damage shall be such that life is safe when they are being hit by the rare earthquakes. Rare earthquakes are defined as earthquakes with probability of occurrence 10% in 50 years. Now, coming to the last type of earthquake, which are said to be very rare earthquakes, very rare earthquakes, whose probability of occurrence is 2% in 50 years. The return period for such earthquakes whose probability of occurrence is 2% in 50 years is 2,500 years. So against these earthquakes, the essential facilities, nuclear power plants, industries containing chemicals with hazardous nature, they should remain operational. They should remain operational. Need not to be fully functional, otherwise the cost will be unaffordable. And then the essential building shall remain life safe, and the ordinary building shall remain near collapse. The difference between near collapse and life safe level is that when the building is at near collapse level, it cannot be retrofitted, or its structural capacity cannot be restored. And when the building is at life safe level, the building capacity can be restored by retrofitting or strengthening. Okay, so this is the difference between life safe near collapse level. Otherwise, even in the near collapse level, life safety life safety is ensured. Okay. Then coming to the explanation of the fully functional. Fully functional means no significant damage has occurred to structural and non-structural components. A building is suitable for normal intended occupancy and use. Operational means no significant damage has occurred to structure which retains nearly all of the pre-earthquake strength and stiffness. Non-structural components are secure, and most would function if utility is available. Building may be used for intended purpose, albeit in impaired mode. इसका मतलब ये है कि इसका थोड़ी सी चीजें डैमेज हो जाएंगी, लेकिन ज्यादातर चीजें फिर भी रहेंगी, और मतलब कोई शीशा टूट गया वगैरह वगैरह वो ठीक है, लेकिन otherwise the building will be operational. Life safe is a level where significant damage to structural elements would have occurred with substantial reduction in stiffness. However, margin remains against collapse. Non-structural elements are secured but may not function. Occupancy may be prevented until repair can be instituted. And near collapse level is a level where substantial structural and non-structural damage, structural strength and stiffness substantially degraded, little margin against collapse. Some falling debris hazards may have occurred. Some falling debris में कुछ चीजें गिर चुकी होंगी या करीब गिरने की होंगी, और इनको दोबारा ठीक करना जो है मुमकिन नहीं होगा. So with this explanation, now you would have seen that we do not design our structures against earthquakes such that they do not crack in any situation. We allow the structures to crack and suffer some damages, because if we intend to design our buildings such that no cracking occurs, no damage is allowed, then the buildings would be very uneconomical, almost unaffordable even for very rich countries. So this is the design philosophy. We design our building with this design philosophy, and we do this because you have seen that the occurrence of earthquakes, there's the probability of occurrence of earthquakes, which is mentioned on the y-axis, is such that for frequent earthquakes it is 50% in 50 years, which means that 50% is non-occurrence and 50% is occurrence. Similarly, for rare earthquakes, the probability of occurrence is 10%, but it means, in other words, that the probability of non-occurrence is 90%. And for very rare earthquakes, the probability of occurrence is 2%. In other words, it means that the probability of non-occurrence is 98%. So when the probability of non-occurrence is 98% and only 2% occurrence probability, it would be highly questionable to design our structure such that no cracking occurs, because initial investment will be very high, and people will not be able to design and construct their structures. The initial cost of the construction will be too high, unmanageable and uncontrollable. For this reason, some risk is always accepted, and this we do in our daily routine life. For example, if you want to travel to Islamabad on a particular day, which is a foggy day, and there is an announcement from the weather department that the fog is of such a nature that accident probability is very high, let's say 90%, and 10%, there is a probability that accident would not occur. Even then, if somebody has an emergency in Islamabad emergency meeting, he would manage to do this, but he would like to have a good vehicle so that even if there is an accident, he is saved. But even then, he would not like to have very, very costly vehicle which is unaffordable and economical. So these type of risks we do accept in our daily routine life, keeping in view all the parameters. So the same has been the design philosophy has also been developed keeping in view all these risk factors. So when a properly designed building gets damaged during an earthquake, it does not mean that the building is failed. If life is safe, then the building has done its job. Okay, next is the building code of Pakistan. In Pakistan, the design criteria for earthquake loading are based on design procedures presented in Chapter 5, Division 2 of Building Code of Pakistan, Seismic Provision 2007, BCP SP 2007, which have been adopted from Chapter 16, Division 2 of UBC 97, Uniform Building Code Volume 2. So the Building Code of Pakistan, if you look at the Building Code of Pakistan, and you compare this Building Code of Pakistan, BCP SP 2007, with UBC 97, except few parts which are related to seismic hazard zoning, the other parts are more or less the same as UBC 97. Because when we were developing this code in 2005, major earthquake occurred in Pakistan. So when we were developing this code in 2006 and 2007, at that time, UBC 97 was the most used code in Pakistan and elsewhere, and the different earthquake parameters which are required in UBC 97 are easily available in Pakistan. At that time, those parameters were not available, but then we developed those parameters for Pakistan by developing a seismic hazard zoning map, which is now part of the Building Code of Pakistan. However, in most recent codes, the Uniform Building Code 1997 is not supported. UBC 97 does not exist as a code now, and it has been replaced by IBC, International Building Code. However, the design parameters, especially the seismic design parameters required in the International Building Code, IBC, are not available in Pakistan. They would require a lot of time and effort to develop those parameters, and for this reason, IBC in the current form cannot be directly used in Pakistan, and we must have to use the Building Code of Pakistan or Uniform Building Code UBC 97 for our structures against earthquake forces. Okay, the total design seismic force imposed by an earthquake on the structure at its base is referred to as base shear V in the UBC 97. And the design seismic force can be determined based on, you have seen in the initial slides that when earthquake hits a structure at the base, basically it is the ground which moves due to the earthquake waves, and because the structure is supported on the ground, the foundation along with the ground also moves. The upper part of the structure cannot move due to inertia and lags behind, and this relative displacement between the roof or the floors, top floors or roof, and the ground causes stresses in the structure, and these stresses must be such that the structure, the resistance of the structure against these stresses must be such that the structure does not collapse. So how do we make sure that the resistance of the structure is more than the stresses induced by this relative displacement or relative moment of the structure. For this, the push at the base of the structure being caused by the ground motion shall be calculated, and this is done using the base shear procedure, which you will see in the next coming slides. This is the basic push of the earthquake at the base of the structure. This can be done by two ways. Number one is the dynamic lateral force procedure, which is covered under section 1631 of UBC 97 or section 5.31 in BCP 2007. These are equivalent sections. And the static static lateral force procedure, section 30.2 of CBC 97 or 530.2 of BCP 2007. These are two procedures outlined in the code. In the dynamic lateral force procedure, the UBC 97 section 1631 include information and dynamic lateral force procedure that involve the use of time history analysis and response spectrum analysis. The details of these methods are presented in section 1631.5 and section 1631.6 of the UBC 97. We'll briefly discuss these two methods. The time history analysis. In the time history analysis, the earthquake recorded motion or artificially generated accelerogram in digital form is applied numerically at the base of the building, and then the response of the structure corresponding to all accelerations recorded at any instant of time is calculated with the equations of motion given in the structural dynamics. In the structural dynamics courses, you would have studied the equation of motion in these things. How can we solve the equation of motion, which is basically a differential equation? If we know the ground acceleration, if ground acceleration is known, the rest of the properties of the structure can be determined. And by solving the equation of motion, at every instant of time, the response of the structure can be calculated. Since when we say that at every instant of time, this response of the structure is calculated, so basically the record of the structure during the whole earthquake duration is calculated. So this record, in other words, is basically a history of the structure during the earthquake, or the response history of the structure during the earthquake. So for this reason, it's called time history analysis, because during the time duration of the earthquake, the response history at various locations of the building can be calculated using the equation of motions, using the knowledge of structural dynamics. So this is basically done like this. The digital recorded data are artificially generated accelerogram in the form of values digitally are applied to the base of the structure in the form of u.g, or ground acceleration. And then the response of the structure in the form of relative displacement is calculated at every instant of time in the form of a history of the building during the time duration of the earthquake. And then these displacements are multiplied with the stiffness of the structure in order to determine the force F. And then the stresses in all part of the structure at any instant of time during the duration of the earthquake are calculated. So this gives a time history. This is very, very, you can see that this is a very rigorous procedure, very difficult, laborsome, and time consuming. And it is seldom done for regular routine structures. This is only done when the structure is of very high importance. Then the time history analysis is done, carried out. The response spectrum analysis. The response spectrum analysis is also a dynamic lateral force procedure. But unlike time history analysis, this procedure is easier. And this procedure has been derived from several sets of time history analysis of different structures. For example, if you have a structure with a certain time period, 0.3 seconds, regardless of the material of the structure or other properties of the structure, if only time, because time period is the fundamental property of the structure with regard to dynamics parameters. So when the time period is known to us, let's say if the time period of 0.3 second will basically represent a structure. So all structures made of whichever material, they if they are having time period of 0.3 second, so we can use the time history analysis of an earthquake and can determine the response of the structure, and there will be a peak displacement in this whole displacement history of the structure. We will record this peak of the structure D1, and we will plot this on a graph with the time period of the structure against peak responses. So for 0.3 second, we will plot this D1 like this. 0.3 second, let's say 0.3 second, this is point D1. Similarly, with the increase in time period of the structure, with the same time history, we can determine the displacement history, and the peak from this displacement history, let's say it is D2, we will determine this D2. Okay, and then D3 against a time period of, let's say, 2 seconds. So with the increase in time period, the displacement may decrease in this manner, which is usually the case. The displacement will decrease when the time period decreases. The reason is that the time histories, the acceleration time histories that we use in this analysis, they are in the near field. They are mostly from the near field region. So in the near field region, the resonance will occur when the time period is small, and low rise structures will resonate in the near field region because the frequency of the earthquake and the frequency of the structure can match. So the displacement will be high for low rise structure. The displacement will slowly and gradually decrease because the time period of 1 second basically taller structure, and tall structure will not resonate, or resonance cannot occur for the time history which is recorded in the near field. So the displacement will decrease with the increase in the time period. And now if we want to design a structure and we want to calculate forces for the structure, so we just can calculate the time period, and on this graph between these two values, we can interpolate and can find out the value of displacement. And once the displacement is calculated, the force K times U or K times D can be calculated, and then it can be transformed into stresses in the part of the structure. So from a similar exercise, a response spectrum, and from response spectrum analysis, from a similar exercise, a response spectrum curve has been developed, and this available in Building Code of Pakistan, which is basically from the UPC 97. So this, you can see the initial branch of this, and then a flat portion of this, and then a lowering down branch of this curve. There are 3 branches of this response spectrum, and the values of this response spectrum can be calculated, and this graph can be used in the response spectrum analysis. Okay, the static lateral force procedure, which is the most used procedure in designs. The basic concept of this static lateral force procedure is that when a building is being hit at the base by an earthquake, so the building foundation will move along with the ground, top of the portion and the roof. They cannot move due to inertia. So this lagging behind the relative displacement will cause stresses in the structure in this form. You can see the bending of the walls. Okay, this can be this behavior can be modeled, or this behavior can be shown to be derived from a force applied at the top of the structure. So this is done like if the base is fixed, if the base of the structure is fixed, and a force is applied at the top of the structure. So it is possible to produce almost same or very close to the stresses produced in this case on the left when the structure is being hit at the base. So in the two situations, when the structure is being hit at the base, or the structure is affected at the base, and if force is applied at the top of the structure, it is possible that they are uh, modeled. The situation, the two situations are modeled such that same kind of stresses are produced. So this kind of thing is basically uh, transformed into this kind of situation where the force at the top is applied and almost the same forces or same stresses are. It is possible. It is possible to apply a force at the top to produce the effect as if it has been hit by the structure at the base. So this is a static lateral force procedure concept. And basically, what we do is that in this lateral force procedure, we basically develop this push base shear V. So all this base shear V is calculated. This base shear V at the base of the footing is the maximum force applied at the base of the footing by an earthquake. This will depend on the zone in which the building is located, the importance of the building, and also the time period of the building, because the time period of the building, the time period of the building is important because the resonance phenomena has been inherently taken into account in this equation. Okay, if the time period is small, then base shear will be very, very high. Similarly, R is another factor which is explained in this slide. So let's see what are the parameters in base shear equation. V is the base shear or push at the base. CV is a seismic coefficient which depends on the seismic zone, and this can be obtained from table 16R of the UBC 97. I is importance factor, which depends on the importance of the building. Again, this is available in the table. R is a numerical coefficient ranging from 4.5 to 8.5. And basically, this is a representative of inherent overstrength and global ductility capacity of lateral force resisting system. R is basically the structural property of the structure, not property of the material. That is the global property of the structure. Like if it is a steel structure, then steel structure has a lot of capability of undergoing inelastic deformation in several cycles during an earthquake without being damaged. So the R factor will be high for steel structure, and base shear will be less for that structure. Because even when a steel structure undergo a lot of stress cycles, then the damage will be in control. Though there will be damages, but the damage will be in control. Similarly, a reinforced concrete frame structures properly designed, if it undergoes several cycles of inelastic deformation, then it will damage, but the damage will be controlled. So that if the damage is controlled and life safety is ensured, even under this damage, in the damaged state, then we can keep R high, because a high R will reduce base shear V, and when base shear V is kept less, then the stresses will be less, and the structure will be economical. So if a structure is being hit by an earthquake, and the structure is of such a nature that the damages in the structure are controlled, happens at controlled location, and they do not put at stake the life safety of the occupants, then R can be kept high. So the steel structures and reinforced concrete frame structures are good structures with regard to the overstrength and global ductility capacity. The damages are very well controlled in these structures. Unlike masonry structures, stone masonry or brick masonry structures, where the prediction that the building will damage and occupants will be safe cannot be done very accurately. So for masonry structures, R must be kept less, so that they are designed against such forces which would ensure life safety. Okay, so the greater the R, the structural, the greater R means more efficient structure with more control damages and more control damages and less base shear in economical structure. Okay, the total design base shear, which is explained on the previous slide, shall not be greater than 2.5 CAI divided by R. So this is the maximum limit on this. If you remember the response spectrum curve, there is a flat portion of the response spectrum curve. Basically, this equation corresponds to that flat curve, flat portion, because the base shear cannot exceed that flat portion. So the 2.5 CAI divided by RW is the maximum limit of the base shear. Once we determine base shear from the previous equation, we'll also determine the equation base shear from this equation, and the base shear calculated from the previous equation shall not exceed this one. Okay, then there is a minimum limit to this. The minimum limit is this one, 0.11 CIW. In addition to the seismic zone 4, well, in addition to these equations for zone 4, there is another equation that the total base shear shall not be less than this thing, 0.8 ZNVI divided by RW. NV is a near source factor, because if it is zone 4, then it is very likely that the building is in very close vicinity to the epicenter. So the near source factor is another factor which, in conjunction with the previous factors, is also applied in the equation. Okay, next we will start the calculation of the base shear V in these steps 1 to 7, 1, 2, 3, 4, 5, 6, 7. Step 1 is site-specific details we would be requiring. Then seismic coefficients will determine, and seismic importance factor, determine R factor, structure's time period, base shear V, and then apply maximum and minimum, determine vertical distribution of V. So first of all, find site-specific details. Following is a list of data that need to be obtained. Seismic zone. So if you know the location of your building, you can determine in which seismic zone your building is located. Then the soil type. Soil type can be obtained from the soil type can be determined from the lab tests. Otherwise, the Building Code of Pakistan and UBC 97 also permits us to categorize soil as SG type, which you will see in the next slides, if there is no data. And past earthquake magnitude is also required. This is required only for the highest seismic zone, zone 4. Closest distance to known seismic source. These two information are required for the seismic zone 4. Otherwise, seismic zone and soil type are enough for all other zones. Okay, seismic zone. Seismic zones is, I explained earlier, that there are 4 seismic zones, and seismic zone 2 is further subdivided into 2A and 2B. Then from these zones, there are seismic zone factor Z. They are called Z factors. Zone Z, if zone is 1, then Z factor is 0.075. If it is 2A, then the Z factor is 0.15. If it is 2B, it is 0.2. If it is 3, it is 0.3, and 4, it is 0.4. So with the increase in zone, the Z factor increases. Soil type. There are 5 types of soil, SA to SE. There is a special SF type, but generally the soil types are SA to E. SA is hard rock, SB is rock, SC is very dense soil, SD is stiff soil profile, and SE is stiff soil profile, but with different parameters. The shear wave velocity is given in this column. So if you are able to determine shear wave velocity, you will be able to determine your soil type. Similarly, with SPT, you can also determine your soil type, and unrated shear strength can also give you some information about the soil type. So after conducting soil test, you will be able to determine your soil type. Okay. And the site-specific details. If site-specific details of past earthquake magnitude are also required, this is then obtained from table 16U of the UBC 97. These are basically three types of seismic source type A, B, and C. Seismic source type A is the one where faults that are capable of producing large magnitude events and that have high rate of seismic activity. And the magnitude of earthquakes 7 and larger very frequently occur here in this region. And the slip rate of the tectonic plate is more than 5 millimeter per year. Similarly, seismic source type B is less severe than this. Seismic type C is the least severe, okay, where faults that are not capable of producing large magnitude earthquake, magnitude less than 6.5, and the slip rate is less than 2 millimeters. So this will be categorized as seismic source type C. So the seismic source type is obtained from this information in table 16U. Okay, a distance to known seismic source is also required to determine additional coefficient for zone 4. Step 2 is determination of seismic coefficients, CV. CV is obtained from table 16R. Depending on zone and soil type, this factor is selected from this table. Okay. For example, you are working in zone 2B, let's say. So this is 1 to A to B. And for seismic zone 2B corresponding to SG type soil, this factor is CV, which is used in the equation for base shear is 0.4. So in this way, you can obtain this very easily. NV is near source factor, which is also required, but this is required only for zone 4. So in the previous slide, we mentioned seismic source type and the distance from the source. Let's say if the seismic source type is A and distance of the building from the epicenter is less than 2 kilometers, then this near source factor will be 2, which will basically double the base shear. And if it is 5 kilometers, it will increase 60%. The base should be 60% increase. And if it is more than 50 kilometers, then the factor will be taken as 1 for all three seismic source types. Okay. Determination of seismic coefficient CA. CA is obtained from table 16Q in the same method, in the same manner as CV, as we discussed for CV. For example, soil type profile is SD, and seismic coefficient CA is 0.28 for 2B. Similarly, near source factor NA in this condition can be obtained in the same manner as we discussed this for NV. Then we have important factor. If we have an hospital, so hospitals are categorized as group 1, where the important factor is 1.25. Okay, hazardous facilities, it's also 1.25. And for ordinary building, this importance factor is 1. R factor, there is some more explanation for R factor. R factor basically reduces base shear V to make the system economical. However, the structure will suffer some damage as explained in the earthquake design philosophy. R factor depends on the overall structural response of the structure under lateral loading. For a structure exhibiting good performance, R factor will be high, as I tried to explain in the case of steel structure and reinforced concrete frame structures. The R values are given in this table, 16N. And these are R values, a closer view of R for special moment testing frame in steel and concrete. The values are 8.5 and 8.5. Okay. And for the masonry moment testing frame, concrete moment testing frame, what are moment testing? This we will learn in the coming slide. Anyway, depending on your type of structure that you choose for your design, you can select R value from this table. The time period can be calculated in several ways. There are two methods given in the code, but this can be determined from a numerical model as well. So method A basically uses this equation T is equal to CTH n power 3 by 4, where CT is these values 0.035 for steel moment resisting frame and 0.03 for reinforced concrete moment resisting frame. These values 0.0853 and 0.073 given in brackets, they shall be used when you are working in a meter system. So if the HN value is taken in meter, then the values in brackets will be used. If it is in feet, then these 0.035, 0.03, 0.02 values will be used. Commonly, we'll use 0.03 as value for time period. Okay. Okay. In step 6, we will check whether this base shear calculated from the equation is shall not be more than this and shall not be less than this. Once we calculate base shear, then we will convert this base shear into a set of forces, and those set of forces will be calculated from this equation. And once the set of forces are calculated, the set of forces will be applied at every story level to produce the same effect as if this building has been hit by an earthquake at the base. So the distribution of forces, the equation is this: Fx is equal to V minus Ft into Wxhx divided by summation of Wihi. I ranges from 1 to n, where n is equal to number of stories. Okay. Ft is additional force that is applied to the top level, to the roof, in addition to the Fx force at that level, when this is only for those conditions when time period is more than 0.7 second. If time period is less than 0.7 second, then Ft is taken as 0. This Ft has been introduced in this equation in order to take into account the change in shape of the structure for larger time period structure or tall structures. Okay, let's now demonstrate this using this example. Here is an example. We have to calculate the base shear and story forces of a 5-story concrete frame building given in the figure. The structure is constructed on stiff soil, which comes under soil type SD of table 16 GFUBC 97, and the structure is located in zone 3. So all the data is given. It is zone 3. I factor is 1. Type soil is D, and loads are masses of weights of the structure are given, and it is SMRF type of structures. You will learn this SMRF, but anyway, it is given in this. Okay. So let's start calculating base shear and then set of forces. First of all, we know that this equation is the basic equation. V is equal to CVI divided by RTW. We will calculate CV corresponding to zone 3. Zone 3 and type soil is D. So we will pick this value is CV. CV required here. CA will be required in the equation for maximum base shear. That value is 0.36. So 0.54 and 0.36. These values will be picked from these two tables. I values directly given as 1. We'll take this value as 1. R factor for SMRF is 8.5. You can see. Time period 0.03. The building is 60 feet high. So 60 power 3 by 4 is 0.646 seconds. Time period is. Weight of the total weight of the structure is this summation of all the weights on all floors and roof. This is 4 into 800 plus 700, so 3900 kip is the total weight of the structure W. 3900 kip. Now we can determine base shear using this equation: CVI divided by RTW, 0.54 into 1 divided by 8.5 and 0.646 time period multiplied by total weight of the structure. This comes out to be 383 kips. The maximum base shear 2.5 CI is 413 kip. So this value 383 kip is less than this. This is okay, but this should not be less than the value obtained from this equation: C 0.11 CAI divided by W, which is 154.44 kips. The value 383 kip calculated from this basic equation is within the range of 413 and 154. So this value is okay. Okay, now we will vertically distribute this base shear. The equation for the base shear is Fxv minus Ft. You will learn this. This is easy. This is not difficult. Okay. Summation of WIHI. Summation of WIHI means weight multiplied by the story height. So 800 multiplied by 12 plus 800 in the next story multiplied by 24 plus 800 multiplied by 36, 800 multiplied by 48. So this summation of WHI in the denominator comes out to be this. Okay. Now we have to see whether FT applies or not. If the time period calculated in the previous equation is 0.646. 0.646. So the time period is less than 0.7 second. Ft is taken as 0. For this reason, Ft in this equation, this Ft is taken as 0 because the time period is less than 0.7 second. Now, if you want to calculate F1, F1 is the force here at this location. Story 1. So this will be this V minus Ft0 and Wxhx, W1 into H1. So 383 minus 0, because base shear is 383, into 800 into 12. 800 divided by this whole. This will give us 27 kp over here, this location. And then the rest can be calculated very easily. For story 5, here at this location, we will start from here in this table. The total height is 60 feet, the weight is 700, Wxhx 700 multiplied by 64 to 200. Summation of WHI has been done here, 138,000 kip. So this divided by this will give us 0.304, and finally Fx will be 116. For all other stories 4, 3, 2, 1, this can be calculated 27, 53, 80, 107, 16. The summation of all these forces shall be equal to the total base shear 383 kip. So the total base shear 383 kip has been distributed in terms of forces along the height of the structure at every story level, like this and this. These forces are applied at the 116, 107, 80, 53, 27. And once these forces once these forces are calculated, the forces can be applied laterally on the structure. And when these forces are applied on the structure, they will certainly give you stresses in the columns, stresses in the beams. Okay, and these stresses or bending moments can be added to the already calculated bending moments from the dead load and live load, and then they will give us a combined effect of the gravity and earthquake. Okay. This is 383 kip. So this has been transformed into set of forces, and now the structure, when moves due to these forces, it will bend like this, and this will cause stresses in the different parts of the structure. Okay, this is, I think, enough for today, and in the next lecture, we will start from this slide number 58, where we will discuss gravity versus earthquake loading in reinforced concrete building. So up till now, you will learn different concepts related to earthquake engineering, and you also calculated a base shear and set of forces that you can apply on your structure, and the forces are calculated using the lateral force procedure. Okay. If you have any question, you can ask your questions. Otherwise, this will be too much if we do.
Excuse me, sir.
Please. What is your name?
Sir, ये अगर बेस शेयर में सखीउल्लाह
Please, Satullah, please. Ask your question.
सर अगर ये बेस शेयर जो है ना उस रेंज में ना आ जाए या ज्यादा उससे आ जाए, मतलब मैक्सिमम से या मिनिमम से कम आ जाए, तो उस केस में आप क्या करेंगे?
अगर मैक्सिमम से ज्यादा आ जाए तो फिर आप मैक्सिमम इस्तेमाल करेंगे, अगर मिनिमम से कम आ जाए तो फिर आप मिनिमम इस्तेमाल करेंगे.
ओके, थैंक यू सर.
Any other question? Any other question? Okay. If there are no questions, so we will leave at this slide number 58, and we'll continue this lecture next time, inshallah. Still, if you have questions, you can come up with your questions next week. We'll try to answer your questions. Thank you. Assalamu alaikum.